Dzień dobry. So now I have to switch again to English. So my part is now modern data center infrastructure solutions, and with the key is energy efficiency. While I know reliability, flexibility, I look for granted. The special focus today is energy efficiency. Okay. I don't know. Looks like frozen. Maybe. Okay, good. Yeah, thank you very much. So I want to I have three parts in my presentation: challenges in the industry, data center power architecture, and finally, I want to go into some details of the UPS solutions. Yeah, we are entering an intelligent world. All things become intelligent. There is a lot of sensing, a lot of connections, and with this, we generate a lot of data, and we need, let's say, a big support in the whole area to back up this data to make the applications live. All this leads to an explosion of the connection rate. We will, let's say, experience 100 billion pieces in a few years. The data consumption will increase dramatically, and also, let's say, the overall content to be transported will increase. That means we will have the demand of a lot of high-power data center, and yeah, so that's... Even the data center itself changes its structure. Today we have more, let's say, operating system on a server, and we have the applications. We have the applications separate. We will more, let's say, enter into a cloud structure, which allows us to use the infrastructure more efficiently, and our different applications are just in the application layers. So we can see this also in the development of the data center, because also this morning we talk about some distributed mainframes, and we now finally arrive in, let's say, organized rows and separating hot and cold aisle, and yeah, working on a modular structure to grow on demand. Nevertheless, let's say energy efficiency, let's say, as I said, is the key of my presentation here. And there is a projection on the left below side that our, let's say, energy consumption of data center will increase. Nevertheless, the, let's say, performance per watt consumed will increase, but as our data demand is exploding dramatically, it will also increase the overall consumption of power. Here is an estimate of, let's say, 2% of the global electricity consumption to be spent in high-power data centers. There are some numbers, some facts from Google from 2014, 4 million megawatt hours. So that's a very, very high consumption. That means we have to focus on energy efficiency, and one part is the server. The other, let's say, important part, which even lasts longer than a server, because the data center infrastructure may be in place for 10, 15, or maybe 20 years, which basically also drives the cost down. The longer we can use the infrastructure, the lower basically the capex per conversion cycle. So we see here 20% of the total cost of the data center is the initial installation, but 60% of the second part, or the 60% is the biggest part, which is consumed in energy. And yeah, so that's why I focus on this part to be optimized. The missing part of the one of the missing part of the OPEX is the operating and maintenance. And let's say the operating and maintenance, clearly on a historically grown structure, can be a nightmare. And so this is something which also has to be addressed. And one part of the operating and maintenance may be also expansions, how to handle that. That is, let's say, a very important item to focus when you do your overall power architecture. Traditional data center, I mean, I was involved in a discussion during lunchtime. Traditional data center, they have a relatively long time to market because you start with the initial ideas, you understand what kind of requirement you have, and when you put a data center in place, you have to also look to the future, so it should be, let's say, flexible for the overall lifetime of the building and infrastructure range. Then we go into the detailed design. We want to achieve a good POE, and clearly, well, the level of performance, which kind of T rating we achieve, which kind of power density, etc., etc. Then we enter the construction phase. We have to do the detailed planning, which also takes some time, and then we do the actual construction at the end, the commissioning, and then the data center is ready for operation, and let's say we enter the maintenance phase, the lifetime. And this time went from the first idea to the getting a data center operational may easily take 2 to 3 years. So one way to address it is to use pre-designed modules in the construction time. Then during the lifetime, as I said, energy cost and O&M is the significant part to optimize. And at the end, we want to have a good availability, because clearly when you operate a data center and your data center infrastructure goes down, that's not what you want, and this will be a big problem. So now I want to focus on the power center infrastructure. And the key part of the power infrastructure is the static UPS system. And here I showed a little bit the evolution. So we may not, in the data center infrastructure, we may not follow the same path as Moore's law, where the performance is increasing, is doubling every year or 2 years. But we still have a significant development behind us. We started some, let's say, 20 years or 30 years ago with diesel rotary UPSs, which were not scalable, which had, let's say, which could not do any power conditioning. Then we entered the area of static UPSs with transformers. Then we came to the transformer-less UPSs. And finally, we arrive in the age of the modular UPS, where I can see through all this time, we were looking at increased efficiency, reliability, and power density. To show you some numbers about efficiency, the light blue curve is, let's say, a very traditional UPS, which is more than 30 years old, with self-commutated thyristors. There was a reasonable efficiency of 90% at the full load point, but then the efficiency went down, and it's even not shown, let's say, below 30%. The efficiency really went down a lot. And with all the steps I showed to you in the previous slide, that was a significant advantage to increase the efficiency. So from the thyristor-based UPSs to the transistor-based UPSs, we had a good efficiency increase. You see the purple curve. And then with the introduction of the IGBT, it improved again. And transformerless IGBT, we touched the 94, 95 line, and now with a modular part, we can go up to 97, and I think in the future, 98 in double conversion, online operation will be no problem. So that's especially, as you can see, the curve shifted to have the optimum efficiency in a very probable operating range of the UPS. So actually, when you said the thyristor-based UPS had an efficiency of 90%, it's not true, because you were working around 40% or less load level. So basically, you run at 80% or whatever. And some of the today's data installation, they even run below 10% load of the UPS, where you can see it really much depends on the generation of the UPS you're using, where it's falling down. Weight and volume reduction was also quite significant. Let's say we can produce 5 times more power out of the same weight in the latest generation, and also with the volume we have 3 to 4 times less volume. And who is driving that? So, and I think this looks like that we are at the end of a road and we cannot get further. I believe we still can get much further, because devices and topologies, it will be a development where we still can achieve more. I just want to use one let's say, keyword, like multi-cell, multi-level inverters. This can give us, or from the device point of view, silicon carbide or gallium nitride devices. Integration is also a very important thing, and miniaturization, this is, let's say, mainly in the IT stuff, granted, but we can also use it more to have a more complex layout of the devices and then achieve much better efficiencies. So here I want to summarize. What do we expect from a modern power infrastructure in a data center? For sure, a high, reliable, safe operation. And when I say 100% uptime, I also mean during maintenance and expansion, and maybe even in failure mode, to be able to recover from failure mode without, let's say, extensive procedure. Clearly, energy efficiency and maintenance-friendly operation is an OpEx driver. Scalability and cost-efficient modules. Scalability is also, let's say, a good thing when you start the infrastructure to, let's say, grow as you need. So that is, let's say, you can find this in the UPS. You can also find it in, let's say, modular data center solutions, where you grow a rack space step by step, and you have the complete hot and cold aisle containment arranged with the in-row cooling. That's a very, let's say, good solution. And I think in the future, the power electronics will be more a long life operation with less maintenance. This is, for example, one let's say, design target from our side, to have a 10 years operation of a system without replacing wear-out parts. And finally, this should lead you to the best cost performance during the whole service life of the data center infrastructure environment. So, one way to do, and this is a very traditional way to do the power infrastructure, is you have a supply from the grid, you have a diesel generator, you bring them together, and finally you feed your load. And this is, let's say, very proven and very much used all over the place. Nevertheless, there are new thoughts. One is coming from the telecom power, let's say, to scale up, to use similar environment like in the telecom power, but with a 48 volt DC, you can only power very low, not too much power. So the key thing is here to increase the DC voltage, put the battery directly to the output. That is one development, but at the end, There was big enthusiasm when the idea came up to increase this voltage, but I would say it doesn't pay off in the whole lifetime because the power you can distribute in DC is limited. All the power supplies must meet the DC input, and so this is a solution which, let's say, did not find a way through, but may be reasonable for very specific applications. Another one is to forget about the power protection during the distribution, just to put it into the server. This is also a possibility to simplify the power infrastructure, but again, the lifetime of the infrastructure may be 10, 15 years. The lifetime of the server is just 3 to 5 years. And let's say, the best way to save energy in a data center is to use a recent server generation which can perform a lot of calculation power for the same electrical power consumption. So I tried to put it together as a model. So clearly you have your TCO, total cost of ownership, and you buy with this TCO a certain availability, reliability, and failure mode behavior. Your CapEx is driven by the architecture of your design and the utilization. I will explain this a little bit later. And the OpEx is the efficiency, how you run it, and the efficiency of the service and maintenance. So here we see all the components of the AC power chain. And I want to go through the next slides, how to organize this. I jumped this slide because I jumped these two slides. So one part is on our output distribution. We want to have discrimination. Discrimination means when I have a short circuit on level 3, the level 3 protection should operate. If I have a short circuit, and level 1 and level 2 should work independently. And so this is one important design criteria. So basically what it tends to means this output distribution should be, let's say, as flat as possible. And so it depends which kind of power I need to distribute, and I will show a little bit later. Another important thing is for the reliability is there's a residual current monitoring. So this gives you always a good information about how is your isolation. Do you have any isolation problem in your system? And so this also helps to simplify the maintenance, especially the high-pot testing. So in order to feed a high available data center, we normally use a dual feed configuration. So here is, let's say, a typical example. There are 2 server rows. In the middle, you have a aisle containment, and you can decide what is hot, what is cold. So either the middle is cold, the outside is hot, or the middle is hot and the outside is cold, depending how you want to arrange it. But key is you have bus bars, 2 bus bars running through, and it supplies, even if one supply is down, it can supply, the server will operate. And this is, let's say, very easy. So normally it's color-coded, and so that's a very good way to do it. What does it mean in terms of power infrastructure behind? So you have, let's say, double the installation. You have a medium voltage feed into your UPS system. You have a generator system in your UPS system, and you distribute the power into the server rack in 2 independent paths. Well, that's very good because we avoid any single point of failure, especially when the power supply in the server has multiple power supplies with certain redundancy. So we really can deliver the power to the server infrastructure, but this price of single point of failure goes with a utilization of maximum 50%, because A and B, even if they share the load equally, they have to be able in emergency mode to take over the power from the other path. So they have to, both sides have to support full power. So now, then you can do an easy arrangement. As I showed, you power each rows in the same similar way. But if you now want to do better, this single point of failure isolation is a quite nice thing. But yeah, here is, let's say, a little bit, I call it the 2+1 redundancy, because we feed the loads with out of 3 UPS systems in a way that always each row will be fed from UPS number 1 or UPS number 2 or UPS number 3. So the load arrangement would be like this. You feed in with 1A, 1 and 2A, you feed in with 2A and 3A, and if you arrange this, you reach a much higher utilization, which means you cut your capex down. And you can do this even one step more by using 4, sorry, the third one is here in the middle. Then you can even reduce the capex more, and a more complex load arrangement, and you can also grow this step by step. So this is just from the architecture point of view, but how should the UPS room look like? Here we show, let's say, some arrangements, and we also look about energy efficiency. Just a thought, if I have, let's say, 3 UPSs and I do the same hot aisle, cold aisle arrangement as in the data center, I could even use passive cooling in the UPS room, could simplify, eliminate the raised floor, and let's say bring the heat evacuation very close to the UPS. And this could be, let's say, a passive heat exchanger to really rely on just the UPS efficiency, which we could tune at 97%. So 3% of your 3 points of your PUE will then be tuned to the UPS. And when I look at today's solution, especially when they are not utilized quite good, it may be much less. So another, let's say, idea where we could play in the future, this is just one leg I showed before, and here is, let's say, some statistics, which kind of power outage you may have. You see, most of the power outages are very short power outages, and they are mainly caused by a failure event and a circuit breaker to trip. So they bring the voltage down. So that's, let's say, the main idea behind that, to avoid this, is the dual feed, because then you don't have the problem at the same time in the same distribution. But anyway, this is very often covered by the hold-up time of the load, up to 10, 20 milliseconds, and later on you need the UPS backup, and let's say for longer power outages, more than, let's say, 15 seconds, normally the genset starts. So you have these 3 things where to play with, and we also developing power supplies. So basically the hold-up time in the future may not be guaranteed as it is today, to design very efficient power supplies. So basically this is something we cannot rely on in the future, but we would cover with the A and B topology without any problem. The core piece, the UPS, with the UPS battery autonomy, which is today somewhere around 5 to 15 minutes on full load, this could be a subject to think about different solutions in the future, like short-term storages. And just one word, lithium-ion batteries could be designed for short autonomy. Then the battery could shrink. And yeah, also The genset is a very important part, and in the previous proposed architectures, in the 3+N, also the genset is shrinking down. Another, let's say, idea is to use the data center, battery for peak shaving and basically to provide grid services. This would be an idea. I even heard, for example, from Norway, that when you go above your licensed power, you have to pay €6 per kilowatt hour as a price. So this is a way to reduce your average energy price when you negotiate with your utility company the right agreement. And clearly, I highlighted the battery because then it would make sense to use a different battery, and then let's say the data center becomes a prosumer. It's a producer of energy and the consumer of energy, and it works like required at that time. So, okay, so this is about our architecture thoughts I want to show to you, and now I want to go a little bit deeper into the UPS. And when I say modular UPS, we should be able to, let's say, hot swap all the modules. And so this is, let's say, easy for maintenance, but also easy for scalability, because to add a module, that is quite easy. You remove the plate, you just plug the module in, and you just tell the system that the module is installed, and then it will be automatically, the power will be automatically upgraded, provided you have the right connections to the power, to the rack. Yeah, well, to be, let's say, another important part is to be, let's say, immune against grid disturbances. And this is, again, the request to use a double conversion of UPS. Then we can support, or the UPS should be able to support a very wide voltage range, and it should handle all the disturbs in a good way. But nevertheless, there are also some, let's say, environmental issues. In emergency cases, you want to provide full power at 40 degrees ambient. Normally, I would not recommend to run the UPS at 40 degrees ambient. And lightning or overvoltage protection and the conformal coating is also a good thing to, let's say, make the UPS reliability higher. The efficiency curve is a function of the load, and we have, let's say, there is always a sweet spot, and if you are outside of the sweet spot, there is a possibility to just run in the modular system, just run some modules, and they have the other modules in standby. So, for example, we do a high power system with relatively small power blocks. This is a 50 kilowatt power block as an example, because, let's say, I believe there is, let's say, the possibility of effective fault isolation. So you have, on the bottom, you see some incoming fuses. So if you have a hazardous failure on one of the modules, you can easily discriminate. You see it's a clean PCB-oriented design, which is easy for automatic optical inspection and ICT, and a very small number of mechanical components and connections. So this is why we believe this is the most reliable way to build a UPS module. So, for example, if you want to use this module in a high-power data center, here is an array. Let's say we go of 4 times 500 kilowatt, and I said, well, my maximum load is 1,600 kilowatt on this system, and I base it on a 50 kilowatt module, as just shown. So when I compare it with a traditional modular system, with a monoblock system, if I have this data, I have here in each cabinet, I have 2 modules redundant, and in a monolithic system, I just have 1 redundant. And if I do my reliability calculations with the numbers marked on the top, I get a relatively good, I get an excellent reliability on the right-hand side, on the left-hand side, and I have a acceptable efficiency, availability on the right-hand side. But nevertheless, when this system changes, then I lost my redundancy completely, and in the let's say small granular approach, I just lose 1 of the 8 redundant modules, which does not change my, let's say, availability statistics. And I mean, the only way to work with this is to reduce the mean downtime to a smaller value, so to have a faster service reaction on the monoblock rather on the modular. So that's why we believe modular is a good way for the future. Clearly, when the second fault happens, the monoblock system is not able to maintain the load anymore, and so that's a clear advantage. So we can see a modular system, even in this high power range, based on a relatively small module power, is a great advantage and gives you the best efficiency in that mode. So yeah, and this is the end of my presentation. The main driver of the power infrastructure, clearly it's the invest and the utilization of the overall infrastructure versus N+N or N+1. Clearly N+1 with a complete fault isolation gives you, let's say, a certain complex arrangement to supply your loads, but it gives you a good capex reduction. Energy efficiency, clearly it's important to run the equipment, to consider the equipment in the real operating mode and not to compare any, let's say, nominal data where you don't operate. Service life on the UPS, I already mentioned it's important how many components you have to replace during the lifetime. Commissioning, installation, maintenance and expansion is also important, which also ask for modular solutions. And finally, cooling and space requirement. I mean, also this, if you organize the UPS room properly, this can be, let's say, very, very much size optimized. Thank you very much for your attention, and let me know if there is any questions. If you have, let's say, deeper questions, you're always welcome to visit us at our booth. Thank you.